Hello, it's me, Miss Wesley, and you guessed it, it's trig time. We left things off in probably one of the most exciting spots that we could have left things off on page 11 of the trig packet, and I just started bringing up some triangles that I'm wondering whether or not they ring a bell from some geometry review. These 30, 60, 90s, and at the bottom of the page you'll see a 45, 45, 90. You can construct a 30, 60, 90 triangle by taking, let's say, this arbitrary equilateral triangle, sides of length 2, and bisecting it right down the middle. You're cutting that 60-degree angle in half to get angles of 30 and 30. These two sides stay at a 2, your hypotenuse, but then this bottom side, right adjacent to the 60 degrees becomes a 1, right, half of 2. And we can use Pythagorean theorem to get the other missing side length, right? So if I know I have a 1 down here, a 2 for the hypotenuse, Pythagorean theorem tells me your missing side is the square root of 3. And these three values should make some sense because you know that there's a theorem that says that if you've got three different side lengths of any triangle, right, the smallest side is opposite the smallest angle. The next, the middle side, right, square root of 3 is about 1.73, is opposite from the next biggest angle, and the hypotenuse always has to be the biggest of the three. Well, let's do some more SOHCAHTOA practice. We'll continue what we were doing yesterday. Find the 6 trig functions. It's worth it to write them down here. So start with 30 degrees. This is our angle in question, and opposite the 30 is going to be the number 1. So opposite over hypotenuse is going to be 1 over 2. Flipping that, you just get the cosecant of 2. What is the exact value of the cosine of 30 degrees? Well, use the value we got for this adjacent side. Ratio, so ratio of adjacent to hypotenuse, is going to be square root of 3 over 2. These values you see coming up a whole lot in exact values with trigonometry, so we're going to start getting used to them. If I flip that, I get 2 over the square root of 3, but we've talked about how you want to keep these denominators rational. 2 square root of 3 over 3 is a good way to leave it. Tangent, TOA, from 30, opposite over adjacent. 1 over the square root of 3, which rationalized gives you the square root of 3 over 3. And flipping this first version gives you the cotangent of just square root of 3 over 1. So those are all your exact values of trig functions for 30 degrees. We can use the same exact picture to get our same 6 trig functions, but for 60 degrees. And you'll see these same values, but some of them flip-flopping the spot that they're in. So for 60 degrees, the complement of 30, you get sine, opposite over hypotenuse, is square root of 3 over 2. Notice this one's sine, this one's sine has become that one's cosine. They match up. So likewise, the sine of 30 actually should equal the cosine of 60 degrees. Does that match up with the picture? 60 degrees, ratio adjacent over hypotenuse, gives you 1 over 2. So it's like we've taken these two rows and switched them for these answers. Here you'll have the reciprocal of 2 square root of 3 over 3 when rationalized, and just the number 2 for the secant of 60. Tangent of 60 degrees, we've got two ways to get this. One way is to do TOA, right? Ratio of the opposite side to the adjacent, square root of 3 over 1. Yesterday, we talked about a special trig identity, that tangent always equals the quotient. It's the sine divided by the cosine. If I divide this by that, the 2's will cancel and I'll get the tangent. Same thing here. If I had divided this fraction by that fraction, I would get this tangent. Cotangent, right? I've got to flip what I just wrote, so 1 over the square root of 3, or I probably should have just put it in a rationalized denominator version, square root of 3 over 3. All right, let those simmer. Those are very important values. Let's go to a 45, 45, 90 triangle. And this one is isosceles, right? These two side lengths are going to be the same. And if I'm just picking an arbitrary number for the length of the legs, 1 is as good as a number as any, right? So by Pythagorean theorem, we can say that 1 squared plus 1 squared equals r squared, and 2 equals r squared. So r is going to equal the square root of 2. So this is a set of side lengths that you should be kind of used to as well. The longest side is going to be about 1.41, or the square root of 2. Well, this, knowing all three sides, enables us to get all 6 trig functions for 45 degrees. And it actually doesn't matter which 45 you go from, because you've got these base angles congruent to one another. So let's go from this one down here, right? Sine, opposite to adjacent. So 1 over square root of 2, or rationalize square root of 2 over 2. Cosecant, probably easiest to just flip this first version and just make it square root of 2. Cosine is going to be the exact same thing because adjacent to hypotenuse is also 1 over square root of 2. So you get square root of 2 over 2 here and just square root of 2 when you simplify its reciprocal. Tangent, right? Easy on the diagram. TOA, opposite over adjacent, 1 over 1. Or you can use the quotient identity. This over itself, the same thing over itself, also gives you 1. Sine over cosine always equals tangent. And if you flip that tangent, you still get a... I seem to be noticing a bunch of repeats throughout the 3 boxes of those exact values. And I want to summarize them down here with something I've been hinting at, but let's just formalize it. Again, this little box here, not as important that you memorize it. It's just a good little tidbit, a good aside that could save us some time. And it can be shown from the right triangle trig definitions that cofunctions of complementary angles are going to be equal to one another. Here's what I mean. Where do you see complementary angles on these diagrams? Well, 30 and 60 are complementary. To get a cofunction, you would either add the prefix co to it or take the prefix co away from it. So sine goes with cosine, right? The sine of 30 equals the cosine of 30's complement. Both of these are a half. What would be the cofunction of tangent? Tangent and cotangent, right? The tangent of 30 equals the cotangent of its complement, and secant and cosecant end up being cofunctions as well. I'll show you how that looks in these identities. The sine of 90 minus theta equals the cofunction, the cosine of just regular theta, right? If I said, what's the sine of 40 degrees in terms of cosine? You would say, oh, these are cofunctions. Sine of 40 equals the cosine of 40's complement. It should equal the cosine of 50. And I might just want to check that just to make sure. If I'm in degree mode, type in sine of 30 degrees, enter. Ooh, and didn't I say 40? So sine of 40. Get a decimal, right? And then cosine of 40's complement, 50, you get the exact same value back. You could try it with secant and cosecant. 1 over the sine of, pick any number from, I don't know, 1 to 90. Sine of 2, 1 over the sine of 2 degrees should equal the secant 1 over the cosine of 2's complement. It should equal 1 over the cosine of 88 degrees. Should give you the exact same thing. So let me fill in those other identities. Where are we at? The cosine of 90 degrees minus theta should equal the sine of its complement, right? So sine goes with cosine. Tangent and cotangent are reciprocals. They're also cofunctions. So tangent of 90 minus theta equals the cotangent of the regular theta. And cotangent of 90 minus theta equals tangent of theta. Secant and cosecant, like I've been hinting at, go together. So cosecant of theta equals the secant of its complement. And the same thing can be written here. Keep that in mind. Again, when it's useful, I'll bring it back up. This thing gets 3 stars. This table is so useful. And what's cool about it is just knowing the top 2 rows of the table gets you the entire pattern, going all the way down for all 6 trig functions. So I'm not telling you, this is something to be memorized, and I'm not telling you got to memorize all 1, 2, 3, 1, 2, 3, 4, 5, 6, all 18 boxes. If you just memorize the top 2 rows, I'll show you how that unlocks the answers for the other slots. So what did we say the sine of 30 degrees was? Well, there's a pattern here. Everything in these 2 rows becomes a fraction over 2. So if you want to fill in the 2 denominator first for all 6 of them, feel free. The numerators go in a pattern. If I look up to the top of the page, the sine of 30 was 1 over 2, and they're all kind of square roots. This one's the square root of 1 over 2, even though I wouldn't really write it that way. The next one's the square root of 2 over 2, and the sine of 60 is the square root of 3 over 2. So it's like you're just counting up with square roots, 1, 2, 3 for 30, 45, and 60 on this table. Now again, I wouldn't put the square root with the first one. I would just call it a half, but you get the pattern. Cosines, what are they going to do? Check above on the page. They do the opposite. The cosines are going to start at the highest. They're going to start at square root of 3, and they're going to count down. Square root of 3, square root of 2. I'll just put for the last one in the last slot a 1 without the square root. Now I'm claiming these 2 rows with a 1, 2, 3, 3, 2, 1 for the cosines get you the others. Well, could we get the tangent by a quotient identity? Tangent always equals the sine over the cosine. I'll write this here again. Tangent of theta, you can always trust it. It's going to equal the answer you got for sine divided by the answer you got for cosine. And it's kind of nice in the table how one sits right above the other. You're taking this fraction, dividing it by that fraction. 1/2 over the square root of 3 over 2. The 2's will cancel in that complex fraction. You get 1 over the square root of 3. And that rationalized square root of 3 over 3. Okay, can you take the sine over the cosine? This one's so quick, right? Tangent, we've said, is just 1, the same thing over itself. And here, if you divide these fractions, you actually end up just getting the square root of 3. So now we've got another row just from knowing those top two. Well, the others are just the reciprocals. So once I've got these 3 filled in, let's flip to get the next row. Flip the sines to get the cosecants. So we've said this before, right? This cosecant is going to be 2, the reciprocal of 1/2. Cosecant of 45 is going to be the reciprocal of square root of 2 over 2, so it's just that. And then the cosecant of 60 degrees should be the flip of this. So it's 2 square root of 3 over 3, which is the reciprocal once rationalized. What about the secant? Okay, so let's take all the cosines and flip them, right? So we'll have 2 square root of 3 over 3 for the secant of 30 degrees. Secant of 45 degrees is the same as its cosecant, square root of 2. And then secant of 60 degrees just gives you the number 2 there. Last row. I say probably your best bet is to flip the 3 tangents, and then you'll be good to go. So tangent of theta here for 30 degrees was 1 over square root of 3. Flip it back into just the square root of 3. 45, tangent was 1. What could be easier? Flip it, and you still have 1. And then cotangent of 60 degrees, we'll have 1 over square root of 3, which rationalized square root of 3 over 3. The more practice with these numbers we have, the better. The more we get used to them, when I ask for exact values, you're going to see your answers will definitely come from this table. And for starters on the next page, or actually just to finish things off in practice, you have your special right triangles to help, because I could just look at this and say, oh, I'm blinking. I know these are all over 2, but I forget which one's a 3, 2, 1 and a 1, 2, 3. We'll do the sine of 30 degrees. Think of a special right triangle. Opposite over hypotenuse, right? Or over hypotenuse, the 2. So it'd be 1 over 2. Then you know you count up square root of 2, square root of 3, and you're going to do the opposite for the cosine. So cosine of 30 is going to be square root of 3 over 2. Cosine of 45 square root of 2 over 2, and then cosine of 60 is 1/2. How many of these could we get to? Sine of 60 degrees. So sine of 60, well, it's on the table, but we'll say square root of 3 over 2. Nice. Tangent of 45 degrees. Divide this by that, right? We don't have it written, but if you divide it, you'll just get a 1. It's the same thing over itself. Cosecant of 45 degrees. Well, that's not on the table, but the sine is, right? It's going to equal 1 over the sine of 45 degrees. Just practicing getting used to these values. So sine of 45 degrees is square root of 2 over 2. If I flip that, I get 2 over the square root of 2, which rationalized just becomes the square root of 2. Okay, so just flip an answer that you already have there. Oh my goodness, I snuck in a quadrantal. How crazy am I? So yikes, a little bit long of a line there, but a unit circle is all we needed. And at 180 degrees, remember, you can use a circle of radius 1 unit, and the x coordinate's going to be your cosine, the y coordinate's going to be your sine. Don't forget that. So sine of 180, we knew this from a couple lessons ago, is just going to be 0. The other 2 should come from the table. Secant of 30, right? We'll flip the cosine and make it the reciprocal, 2 square root of 3 over 3. Cotangent of 30. You have to admit this is kind of fun, right? Cotangent of 30, let's take the tangent, which would be 1 over the square root of 3, and let's flip it. The cotangent of 30 should just be the square root of 3. A little bit with cofunctions to finish things off. Can you write the function in terms of its cofunction? Well, sure. What's the cofunction of cosine? It's going to be sine. And it wouldn't equal the sine of 52. It'll equal the sine of 52's complement, right? So sine of 90 minus 52 or 48 degrees. It doesn't say you have to solve or estimate or approximate. You're just leave it in terms of its cofunction. What's the cofunction of tangent, right? It'll be cotangent. So what this helps with is, if I see an equation like 12, tangent and tangent, same exact thing, you can actually solve this just by setting the 2 expressions equal to one another. It's kind of easy. Just get theta by itself like you would get an x by itself. But when you see a question like 13 where you have cofunctions, it's not that the 2 arguments are equal, right? Theta plus 4 degrees doesn't necessarily equal 3 theta plus 2 degrees. But if you added them up, what would you have? You would have 90 degrees. Because these are cofunctions and they're equal to one another, their arguments are going to be complements. Okay, it's been my pleasure. Start working with that table, right? Copy, if you see a bunch of exact value questions, copy down that table. Talk to you soon.